Hi, I'm Colin. In this module, we're going to briefly revise the concept of a derivative and then find the derivative of the square root function using two important methods. One is called differentiation from first principles, and the other is a much quicker shortcut that involves using a formula called the power rule. Our goal is the following. We want to show that if we have y as a function of x, given by the rule y equals the square root of x, sometimes called the square root function, then its derivative is the function 1 on 2 root x. Note that we can also phrase this as if we differentiate the function root x, we get 1 on 2 root x. This notation of d dx is attributed to the famous scientist and philosopher Gottfried Leibniz, whom, along with Sir Isaac Newton, discovered calculus. Because Leibniz and Newton discovered calculus around the same time, but completely independently of each other, they both invented their own notations, both of which survive to this day. Newton's notation is relevant for when the original function is written as f of x as opposed to y. Here, the derivative is written as f dash x or f prime x. You should become familiar with the different ways in which derivatives can be expressed, since both are commonly used in the mathematical sciences. Okay, with this basic terminology out of the way, let us now revise some fundamental concepts about derivatives. When we differentiate a function, we produce another function called its derivative, which essentially tells you how steep the original function is at each point. Specifically, it tells you the slope of the tangent line to the original function at the point. So here, the y values of this derivative tells you how steep the original function y equals root x is for every x value in its domain, by telling me the slope of the tangent lines at each point. For instance, if I evaluate the derivative at x equals 1, I get 1 on 2 times root 1, which simplifies to just 1 on 2, or a half. What does this number mean? Well, it's precisely the slope, or the rise over the run of the tangent line to the original function at x equals 1. So here, for every 2 units that I run across, I have to rise up 1 unit. This ultimately tells me that at the point 1, 1 on the curve, the independent variable x is changing twice as quickly as the dependent variable y, or f of x. Therefore, the derivative ultimately tells us the rate of change of one variable with respect to another, which should come as no surprise, since calculus is often regarded as the mathematical study of change. Alright, with all of this said, it remains for us to show how we differentiate the square root function to get its derivative 1 on 2 root x. The first method we'll use is called differentiation from first principles. The phrase first principles comes from the fact that we use the fundamental definition of a derivative that involves a limit. You will have already seen this formula in your lectures, but let's briefly revise this. For a function f of x, its derivative at some point, which is simply the slope of the tangent line to the curve at that point, can be roughly approximated by the slope of a secant line. The slope of this secant can be expressed as the following. Using the gradient formula for straight lines, which some of you may know as the y2 minus y1 over x2 minus x1 formula. Now, as the constant h shrinks down to 0, which we express using a mathematical construct called a limit, the slope of the secant approaches the slope of the tangent, which is precisely the derivative. Using this formula here, to compute the derivative of any function is known as differentiating from first principles. Here, our original function f of x is the function root x, so let's make that substitution. Now recall, with the f of x function notation, whatever is inside the brackets represents the input for the function. So f of x plus h therefore just means, rather than square rooting the input x, we're square rooting the input x plus h. Thus we have the following. Our goal now is to manipulate this expression until we're in a position to let the constant h go towards 0. The reason we can't simply substitute h to be 0 immediately is because we'll get a 0 denominator. Now, an algebraic trick that we can employ here to kick things along is to do the following. We're going to multiply both the numerator and denominator by the expression root of x plus h plus root x. This is certainly mathematically valid, because I'm multiplying both the top and bottom by the same thing, which means I'm effectively not changing the value of the original fraction. Alright, observe that by doing this, we now have a difference of two squares scenario in the numerator. Now, expanding the numerator using the difference of two squares shortcut, we get the following. And then the x's cancel away. So we're just left with h in the numerator. This is where the magic now happens. The h's then cancel away, so we'll no longer have a lone factor of h in the denominator. And this means we're now finally in a position to evaluate the limit and set h to be 0. This leaves us with 1 on root x plus root x, which simplifies to just 1 on 2 root x. Thus, we've shown that the derivative of root x is 1 on 2 root x. Differentiation from first principles is generally difficult. You'll find that you would have to often employ some algebraic ingenuity to help you differentiate even the most basic functions. Thankfully, hundreds of years of mathematical progress since the discovery of calculus means that you rarely need to differentiate a given function from first principles. Instead, there are a small army of differentiation rules we now have at our disposal that makes differentiating even very complicated functions relatively easy. The rule we're going to use to find the derivative of our square root function is one of the most important rules of differentiation, called the power rule. It states that if the function is a power function, that is, x to the power of some constant, n, where n can be any real number that's not 0, then the derivative of the function is obtained by firstly bringing down the power n to the front, and then we subtract off precisely 1 inside the power. For our square root function, it turns out we can employ the power rule, but we must first write the function in the form x to the power of some number. Now, from your studies of the index laws, you know that square rooting is the same as raising to the power of a half. We now use the power rule to differentiate x to the power of a half instead. Firstly, the power of a half comes down the front of x. And we then subtract off precisely 1 inside the power, which gives a half times x to the power of negative a half, which can be written in the following form using another index law, which can finally be simplified to the following. Since raising to the power of a half is, again, the same as square rooting. Thus, once more, we've shown that the derivative of root x is 1 on 2 root x. Now, before we finish, an important thing to note is that these two methods are not completely independent of each other. In fact, you may be surprised to discover that the various shortcut rules for differentiation that you encounter in your studies are all derived from first principles. But in practice, we always use shortcut rules to differentiate a function, since differentiating from first principles is generally much more difficult and time-consuming. However, for the purposes of learning and understanding derivatives, it's important to know how to differentiate a function from first principles. Alright, I hope you found this module useful. See you next time.